Hello everyone, it's Kevin, one of the workshop leaders for Chemistry 10401. Now today I'm going to be covering Chapter 17, which is called Additional Aspects of Acid-Base Equilibria. Specifically, the main focus of today's video is Section 1 of Chapter 17, which is called the Common Ion Effect in Acid-Base Equilibria. Now before I actually get into this section of Chapter 17, I just want to review something that we learned from Chapter 16. Now, I'm just going to throw out there a very hypothetical scenario, and I've drawn it out already for you guys here. So imagine right here that you have a bucket that just contains H2O liquid. Now I think that for most of us it's kind of pretty easy to visualize. You know, you're at home, you take a bucket, you place it on your counter, and then you take a cup of water and then you toss it inside of that bucket. So this is what we have right now. Now just assume for the purpose of this video that the only thing inside this bucket is just H2O. There's nothing else. If I was to ask you the question, what reaction is going on inside this bucket, you would tell me that there is only one reaction going on in here. And that reaction is called the self-ionization of water. So when you have water by itself, it turns out that liquid molecules actually do react with one another. And this is again something that you guys learned in Chapter 16. If I was to write out the reaction for this, the self-ionization of water would look like this. It's H2O liquid plus H2O liquid. And that comes into equilibrium and forms H3O plus aqueous plus OH minus aqueous. So this right here, the self-ionization of water, is just a reaction that occurs between two H2O liquid molecules. So what's going on here is that inside this bucket, water molecules are interacting with one another and you're forming a hydronium ion and a hydroxide ion. Guys, remember this right here is the hydronium ion, which by the way is an acid, and this right here is the hydroxide ion, which is of course a base. Now, if I was going to write down the equilibrium constant expression for the self-ionization of water, it would be equal to this. Kw, just a little recap, it's always going to be the products over the reactants raised to the stoichiometric coefficients. And remember that solids and liquids do not show up in equilibrium constant expressions. So in this case, the equilibrium constant for this reaction right here, the self-ionization of water, it's going to be the concentration of H3O plus to the first power times the concentration of OH minus to the first power. And we learned in Chapter 16 again, just a quick review, that at 25 degrees Celsius, this value is always going to be equal to 1.0 times 10 to the negative 14. Now, before I go any further, let me just interpret this number right here. What does this number mean? That the equilibrium constant for water is 1.0 times 10 to the negative 14. Now, we already know that K, as we've learned from Chapters 15 and 16, K is always called the equilibrium constant. Equilibrium constant. And you guys know that the equilibrium constant always, it's trying to relate the amount of products to the amount of reactants at equilibrium. But more importantly, you can actually interpret the equilibrium constant as being a tendency for a reaction to occur. The tendency for a reaction to occur. Now, this is very, very important. Now, I'm trying to shift so you guys kind of understand what these values actually mean. So like I said before, K is the equilibrium constant, but now let's think of K as being a tendency for a reaction to occur. You guys see how this number is 1.0 times 10 to the negative 14? That's an incredibly tiny number. That is small, 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 small. So if we're saying right now that the equilibrium constant can be interpreted as a tendency for a reaction to occur, we can say that this reaction right here has a very low tendency to occur. So when I look at this reaction right here, this reaction has a very low tendency to occur. That means that it's very rare to see H2O liquid molecules interact with one another to form H3O plus and OH minus. That does not mean that this reaction does not occur. It just means that it has a very low tendency of occurring. Like I said, now try to think of these equilibrium constants as being tendencies for reactions to occur. So like I said, 1.0 times 10 to the negative 14, that's a very, very, very tiny number. to the negative 14. And since it's such a tiny number, that means that this particular reaction up here, the self-ionization of water, has a very low tendency of occurring. Now let's do something very quick. Let's flip this reaction and see what happens. So if I flip this top reaction, if I flip the self-ionization of water, I get this. I get H3O plus aqueous, the hydronium ion, plus the hydroxide ion, OH minus aqueous, and that's going to come to equilibrium and it's going to form H2O liquid plus H2O liquid. Notice that this reaction right here is literally the flip of this reaction. So the relationship between these two right here is that I flip them. If I was to ask you again, we know if we were going to write down the equilibrium constant for this expression right here, for this reaction, we know that K would be equal to 1 over the concentration of H3O plus times the concentration of OH minus. Now, if I was actually to tell you what's going to be the equilibrium constant for this expression, we learned in chapter 15 that whenever you flip a reaction that goes to equilibrium, you can take the value of K and take it and divide it by 1. Or, I'm sorry, not divided by 1, but it's 1 over that particular value. So if I was going to look at the K for this expression, it would be equal to 1 over Kw. Now again, we know that Kw is 1.0 times 10 to the negative 14, and that equals 1.0 times 10 to the positive 14. Now look at this value right here. You guys see how this number is an incredibly huge number? We're talking now something that's to the positive 14. That is a humongous number. Now again, the equilibrium constant for this expression is a humongous number. This is a very big number. Very big number. Now, what does it mean if the equilibrium constant for this expression is a very big number? I told you guys before, think of equilibrium constants as tendencies for reactions to occur. So if we look at this reaction, and this reaction has an equilibrium constant that is a very big number, that means that this reaction has a very high tendency to occur. So just notice this. Now I have these two reactions right here. And the main point that I want you guys to take away from this video, at least from this little recap that I'm doing right now, is that when I look at equilibrium constants, not only can I interpret them as being tendencies for reactions to occur, but they also tell me which reaction is going to be favored. You guys see how, in this particular case, since K is such a tiny little number, we know that this reaction has a very low tendency to occur. When I look at this reaction, which is literally the flip of this top one, this has a very high tendency to occur. Now, very important, what I want you guys to notice is that whenever, you guys see how this reaction is telling me that whenever a hydronium ion comes in contact with a hydroxide ion, it's always going to react and it's always going to form H2O liquid molecules. How many? 2 of them. So take that away from this. The most important part of what I just did right now was that whenever H3O plus comes in contact with OH minus, or whenever OH minus comes into contact with H3O plus, it will always form H2O liquid. They will always form that. So whenever these come in contact, they always form H2O liquid. So whenever these are in contact inside of a solution, they're always going to interact with one another, and they're always going to form H2O liquid, since it has such a very high tendency to occur. Now again, that was just a small recap of something you guys learned in chapter 16 of your textbook. Now, just to continue with some of the other stuff that you guys learned inside of that chapter, we also continue with that same example that I was giving you. You know, you have a bucket that just contains something like H2O. And, problems in chapter 16 said, well, let's say I have a bucket of water and I toss in a weak acid, something like acetic acid, CH3COOH. So I have this bucket that has just water, and I toss in a weak acid inside. And now we know that what happens when a weak acid comes in contact with water? We can write down the following expression, the following reaction. CH3COOH plus H2O goes into equilibrium, and it forms, if this is the acid, we're going to form its conjugate base, which is CH3COO- plus H3L plus. And now, typically problems like this would say, what if I have a solution that has a concentration of 0.10 molar of acetic acid, CH3COOH? What is the pH of this solution? Now, this is how problems were usually phrased for chapter 16. And this, for example, this is a very easy example. I can just set up a regular ice chart in this case. And this should be secondhand to you guys. It's very easy. Initially, I have a concentration of 0.10 molar acetic acid. You guys know that H2O liquids, these do not show up in equilibrium constants. 0 molar, 0 molar. The reaction is, of course, going to shift in the forward direction, minus x, plus x, plus x at equilibrium. And of course, it'll typically give you the equilibrium constant for this equation, 1.8 times 10 to the negative 5. And then, of course, you just do regular solve for the value of x. X squared over 0.10 minus x equals 1.8 times 10 to the negative 5. And of course, if I'm trying to find what the pH is, I have to solve for the value of x. Because at the end, the value of x equals the concentration of H3O plus inside of the solution, and then you take that value, whatever value that is, and you plug it into the pH formula. pH equals negative log the concentration of H3O plus. Now, again, very simple problem, and this is how usually problems are phrased in chapter 16 of your textbook. I have a solution that has a concentration of 0.10 molar acetic acid. What's going to be the pH of the solution? Again, you set up a regular ice chart, solve for the value of x, plug it into the pH formula. Very simple problem. Now we're going to move on into what's covered in chapter 17. Now, chapter 17 is a little bit different than chapter 16, because now in chapter 17, what they're asking us is, what happens when we mix more than one component in a solution? Now, just to show you guys what this means, you guys see that here, there's only one component inside of the solution. This is just really the acetic acid, because the acetic acid is what you're throwing inside of the water. Now what happens if you're mixing several components together? So in this case, I'm only mixing acetic acid, I'm throwing it in with water. But that's really the only thing that I did here. Now, chapter 17 is really questioning, it's almost the exact same thing as chapter 16, but now you're mixing more than one component. So now you're dealing with solutions that have various components to them, but you're still asking the same exact question. What's going to be the pH of the solution? That's going to be that. And I'm going to stop this video now, and I'm going to continue it on the next one. And we're going to keep on, and we're going to continue chapter 17.